with a little review of derivatives. So here I have a parabola, y equals x squared. I hope you are all very good at finding that derivative, that its derivative would be 2x. So what I have on this applet that I made in GeoGebra is I have x squared here, and I've drawn a tangent line, and then as I drag the point along the parabola, this program graphs the slope. So for example, right now, it's at the vertex. Can you see the slope is 0? It's drawing a point, that blue point right at 0. But when I go to 1, its slope is 2, so it made this point. But as I dragged it along, it graphed all the points in the middle. Now we know that the derivative of x squared is 2x. Can you see that the blue line that's getting drawn is a straight line? Looks like it has a y-intercept of 0, it does, and it has a slope of 2. So the blue line that got drawn as I dragged all those points along became 2. So now we're going to learn some derivatives of harder looking functions. Ones that we can't use the power rule to figure out. The first one, this is the graph of e to the x. Now you can't bring the x out in front and subtract 1 because the power rule only works for x to the power of something, not something to the power of x. So what I'm going to do here is I'm going to take this point and drag it along, and I want you to see if you can figure out what the equation of the blue graph is. So what is happening here is as I'm dragging it along e to the x, it's figuring out the slope of the tangent and plotting that as a blue point. What do you notice? It's exactly the same. This is like when you learned about e in logarithms, it was just sort of like a weird number. And then there's like, oh, there's a natural log button. Okay, it's just like a weird number. This is why this weird number is so cool. What is the derivative of e to the x? E to the x, which I'm going to tell you is going to mess with your brains. Because this is the only thing in calculus where they say do something, and what you do means keep it the same. Can you see that messing with your brain? Find the derivative of e to the x. It's e to the x. And that will cause problems for us mentally. But this is what makes the number e so special. This is the only thing where you take the derivative and you get exactly the same thing that you started with. No other function does it. So here we have our first new derivative of the day. Our second new derivative of the day. This one's going to be a little bit harder to see, to figure out. But here's the natural log graph. I am going to drag it along here, and it's going to make a new graph, and you have to see if you recognize it. There we go. And this is hard to recognize because yes, it is only half of 1 over x, right? Because the other part of 1 over x would be over here, right? And you don't have that because the log graph doesn't exist. So the derivative of the natural log of x is 1 over x, but I guess technically this is only for x values bigger than 0, because the natural log of x doesn't exist for x values less than or equal to 0. Okay? This one is also going to mess with your brain because it looks so different than what you started with. You started with natural log of x, you get derivative of 1 over x. At least with the power rule, you started with an x cubed, you got an x squared. There was like a pattern you could really see. These ones are a little bit different. But now we can do all sorts of derivatives with them. And we can do all the same derivative rules that happened before. Did it matter when there was a number in front of 2x cubed? The rules still stayed the same, right? You brought the 3 out in front, the 2 stayed there, and then you subtracted 1 from the exponent. Does it matter that there's a 4 in front of the e to the x? No. When you do the derivative, you get 4e to the x. Exactly the same. If you had a 3 in front of your natural log, that 3 would stay there. The derivative of x cubed would be 3x squared. And the derivative of natural log of x would be 1 over x. So we would get 3x squared plus 3 times 1 over x, which is the same as 3 over x. And this is where I'm going to tell you calculus can get complicated because we're going to learn derivatives of a whole bunch of functions. And you're going to have to know them very, very well so that you can quickly see the derivative, write it down. Okay? This is also interesting because using the definition of a derivative, we probably wouldn't be able to figure out the natural log of x easily. So that if you were taking advanced calculus in university, this might be something that gets looked at more in depth. How exactly did someone figure this out? Other than looking at the graph and saying, hey, everything matches up. And now we can start mixing in log laws. I just want to do this one. I don't even want to click a log. This one, you have a derivative for natural log, but only if it's natural log of x. You have a derivative for e to something, but only if it's e to something, not e to something inside of something else. We get to crazy things inside, yeah, that's all coming, don't worry. But at this moment, this is not in a form that you can take the derivative of. It's not a log by itself, and it's not an e to the x by itself. So we have to play around with this, rearrange it to see if we can get it into a form that we do know. What could I do with this function? Think of your log laws. You have a log law with exponents, right? What does your log law say if you have an exponent? You can bring that exponent out in front. Why is that helpful? What's natural log of e equal to? Remember, logarithms solve for exponents. What is the base of natural log? It's not written, but you imagine a little base here of e. If logarithms solve for exponents, what you're really thinking is e to what exponent equals e? 1. Natural log of e is 1. So we really have this equation instead of the complicated equation. What's the derivative of 5x? Just 5. And we're done. So we need to know our previous manipulations, because we're going to need to manipulate questions until we get it into a form that you're allowed to use a derivative rule. So in this case, we needed to use our log lines. I think you can do this one on your own. I'll put up the answer in a bit. Okay, how did you do? Did you get the slope of the tangent with 1? And you get y equals x plus 1 for the equation of the tangent? If you wanted to find the equation of the normal, you could as well. But it didn't ask for the equation of the normal.